What did the receiver say to the radio wave? Ouch, that megahertz. You want entertainment, you want comedy, you got it. In this episode, we're going to talk about radio communication, which is option F1. And when we're talking about radio communication, we talk about any type of communication that uses electromagnetic radio waves to transfer information. And so we're talking about TVs, mobile phones, wireless internet, satellite radio, all of these, anything basically that communicates wirelessly. And that communication is done with electromagnetic waves. And we say radio waves, but now with a lot of the newer devices we use frequencies that are not just in the radio wave frequency. We use microwaves and some of the other wavelengths in there as well, not just the radio wave frequency. But as you should have learned in the previous units, the radio wave is made up of an ever-changing electrical field and ever-changing magnetic field that are perpendicular to each other. And they are also traveling at a 90-degree angle to the direction of propagation, as you can see in this diagram that we have right here. So we have our B field, our magnetic field. We have our E field, our electric field, traveling at 90 degrees, and both traveling at 90 degrees to the direction of propagation as it moves through time and space. Now, the idea behind radio communication is that you have this electromagnetic wave set up. And it's established most easily by a simple oscillating circuit. And you take a power source, an induction coil, and a capacitor, and you can cause the electrons in that to oscillate back and forth. And as we know, anytime you have a moving current or an oscillating current, the field around that current is going to be changing because the electrons are moving back and forth. As those electrons are kind of sloshing back and forth in the alternating current, that electric field is changing. That changing electric field is, of course, going to induce a magnetic field, which is going to be changing. And that changing magnetic field is then going to induce the changing electric field to keep the electromagnetic wave going. And so in this way, we can create an electromagnetic signal. And you have your antenna. This is an antenna. And it's connected to the circuit. And you have all your little electrons. And those electrons oscillate up and down, up and down, up and down, up and down within that antenna. And as they oscillate up and down, they're creating or they're establishing these electromagnetic waves, which are then, of course, going off in all directions. Electrical signal. But then, at the other end of this, you have to have something to receive that signal. And the thing at the other end is almost like to the receiver. You have another antenna. Here's our other antenna. And it has electrons in it. And as these waves hit the antenna, that electromagnetic energy causes the electrons in the antenna to oscillate up and down. That oscillation establishes an alternating current, which goes to the receiver. Now, because the electromagnetic radiation usually travels out from a fairly good distance, by the time it gets to the antenna, it's generally very, very weak. The signal strength is much, much smaller than what it was sent out at, and so you also are going to have a pretty significant signal amplifier wired into there as well. You have generally an amplifier at the output end, and you have an amplifier at the input end to jack up the strength of that signal so that it can be turned into something meaningful. But in order to send information, we need more than just a signal. Because if you just send out that signal, all you're going to get is some tone. Just a generic, flat, single frequency tone. So in order to transmit actual information within our electromagnetic wave, we do something called modulation. We modulate the electromagnetic wave. Back when it was just Morse code, they just turned on the signal and turned it off. So it was on, off, very easy. We've moved fairly well beyond that at this point, and so we have to affect this. And the first way that we do this is through what we call amplitude modulation. And you might recognize the initials there of amplitude modulation as one of your favorite radio frequencies, AM. And we could also do it through what we call frequency modulation, or FM. Whoa. And so, regardless of whether we are using AM or FM, we have a carrier wave and a signal wave. The carrier wave is the base wave. It's the wave that, when you're talking about the frequency of the radio station, that's the frequency of the carrier wave. The modulating wave is the wave that gets put onto it to transmit information. The modulating wave is where the actual information is contained, and it's superimposed on top of the carrier wave. So in amplitude modulation, the frequency of the carrier wave is constant. Okay, we don't change the frequency. So in amplitude modulation, frequency constant. Okay, frequency constant in amplitude modulation. The signal wave is used to vary the amplitude of the carrier wave. And so you can see here in this diagram, here's our signal wave right here. This is our base wave. We take this wave here and we add it to the wave here and we modulate it. And you can see on the right the wave that you get, that's the net wave. That's the resultant wave of those two together. And so that's the wave that actually gets sent out. When this wave gets received by the antenna, there's then basically electricity. There's a circuit in there that breaks this up and it pulls out the signal wave so that it has just the information. It can then take that information and turn it into music or television or whatever it happens to be. Now, when we have a wave being modulated, you're always going to end up with additional waves that get produced, and those are what we call sidebands. Sidebands you're always going to have them. They always occur. It's just a component of this process of modulation, and so the process then becomes, how do you deal with them? And our additional frequencies, just real simply, we can calculate here with our AM. It's the frequency of the carrier minus the frequency of the signal wave plus the frequency of the carrier, or frequency of the carrier plus the frequency of the signal wave. And so this gives you your sidebands, one at a higher frequency than the carrier and one at a lower frequency. And so this, you get what we call a power spectrum, and it looks like this. So here you have the frequency of the carrier wave, and then you have a sideband here to the right and a sideband here to the left. And this area right here and this area right here, that change in frequency or that difference in frequency on either side is the same. And as you look at this power spectrum, one thing to keep in mind when we're talking about these, we're using what are called decibels. Okay, same thing we talked about with sound. And decibels are a logarithmic scale. And so what that means is that when you increase the power by 1 bell, you're actually increasing it by a factor of 10. Okay. What we call, whoops. And so with this, that means that because of the sidebands, you have to actually have more than just the frequency at which you're transmitting. You have to have what's called a bandwidth. And that bandwidth has to encompass both the carrier frequency and the sidebands for any given radio station, if we're talking about radio stations, frequencies, so that they don't overlap, so they don't interfere with each other. And with an AM station, you're never going to have a bandwidth that needs to be more than about 9 kilohertz. You just won't. The sidebands won't be that far away, and so you have a bandwidth of about 9 kilohertz to cover any possible overlap that you might have. And so it's important to realize then that that's why you have to have some distance between the frequencies of radio stations. You're not going to have them, when you're turning the dial, it's not going to go from 98.5 to 98.6 or AM 550 to AM 555 and have two stations that close to each other, because there would be that overlapping of the bandwidth, or excuse me, of the sidebands, which would cause interference in the signals. Then we have frequency modulation, or FM. And just like with our amplitude modulation, where the frequency was uniform, in frequency modulation, the amplitude of the carrier wave is kept constant. Okay, see how that works now? We're modulating the frequency, keeping the amplitude constant, whereas before we were modulating the amplitude, keeping the frequency constant. And you can see in our diagram here, we have our signal wave and our carrier wave. Again, the signal wave is where the information comes from, and our modulated carrier wave, if you look closely, you can see how we have a higher frequency here, and then the frequency drops here, and so you have, again, a pattern of interference that's causing modulation, and in this case we're modulating the frequency. And in an FM signal, the carrier wave is going to deviate from its original frequency by some amount we're going to call delta F. That delta F is known as the peak frequency deviation. And that peak frequency deviation is then going to affect the maximum range of an FM signal. So with our sidebands that we talked about previously, that's going to give you a range of frequencies in AM. With FM, we're going to have a range of frequencies because of the change in frequency caused by the signal wave. And that range of frequencies is given by these two expressions down here, where our frequencies are simply the original frequency, the carrier wave frequency, plus and minus that peak frequency deviation. And then an FM signal also has what we call a modulation index. And with our modulation index, it's kind of a measure of how many sidebands will be produced, and it's related to those two frequencies that we just calculated, and it's also related to the actual carrier frequency. And so the modulation index is equal to the difference in the maximum and the minimum frequencies. Okay, so that was our F plus delta F and F minus delta F, divided by the frequency of the carrier. And so the larger this number, the more sidebands get produced and the wider the bandwidth has to be. And so for any given signal, our bandwidth is going to equal twice the sum of the peak deviation plus the highest modulating frequency. And so that really gives us our bandwidth. And so for FM stations, you actually need more space between the stations. You need more distance between the frequencies than you do with AM, because the bandwidth that's taken up by a single FM radio station is going to be much wider than that taken up by an AM station. And because they need more bandwidth, you find that your AM stations need about 9 kilohertz per channel, while FM bandwidth is about 200 kilohertz. Now, if you look at the AM and FM stations on the dials, you'll notice that AM ranges from about 550 to 1600, while FM ranges from about 98 to 106 or 107. But what you need to realize is that while these are the station frequencies, the AM stations are in kilohertz, while the FM stations numbers are in megahertz. Okay, so that's why even though these numbers are bigger, the coefficients are bigger, they're actually smaller frequencies, larger wavelengths. And so even though there seems like there's a smaller number in between some of these stations, it's actually a larger number. And so you can have a station at 98.7 and 98.9, and that's 0.2 megahertz difference, but it's 200 kilohertz, which is the difference here. And that's why if you notice, a lot of radio station tuners actually go up by 2s. They don't stop on the 0.1s. They go up by 0.2. Now, one of the benefits of FM, one of the benefits of AM is that they generally have a much larger range, and part of that is because of their longer wavelength. As they travel up and away, they actually reflect off of the ionosphere and travel back down towards Earth. And so if this is our ionosphere, here's the blue planet, our AM waves will travel here, reflect off of the ionosphere, and back to Earth, and so they can be transmitted over much larger areas. Some bandwidths actually, back before there was quite so much interference in the air at night, when there's very little electromagnetic radiation, you could often get channels from across the ocean because there was so little interference if you had a strong enough receiver, because those signals were going off the ionosphere, whereas FM, with their lower frequency, travel right through and pass off into space. But the AM signals don't tend to be as high quality, and you know this if you've ever listened to an AM radio station versus an FM radio station. The AM waves are much more susceptible to noise and to interference from other sources of electromagnetic radiation, whereas the FM waves will give you a much clearer noise-free signal because of the higher frequencies. And then you have cost, and it's obviously always about cost, and now FM receivers are obviously much more cheap to make, but they're still more complex. An AM receiver is a very, very simple thing to create, to design, to wire up. Whereas an FM receiver is a little more complex, a little more costly. And actually, an AM receiver is not that difficult to make. it only takes a couple parts. You have your antenna, which sometimes is called an aerial. It's just a long conducting rod, a long piece of metal that the electrons can oscillate in. You have what we call a tuning circuit, and it's a circuit that's generated to resonate at a particular frequency, which is whatever the frequency of the AM station is. That tuning circuit, you actually in the radio in your car, you can change what frequency it resonates at, so you can change the station. You have the amplifier, which of course increases the strength of the signal. You have your demodulator, which removes the carrier wave. And then you have your amplifier that actually amplifies the sound to the loudspeaker. So there's not a whole lot to our AM receivers, whereas with our FM it takes a little bit more. So there's your AM FM. Have a great day.